So Gauss law, we have started. So it is nothing but total electric flux passing through any closed surface, which will be equal to what the total charge within the surface. Within the surface. So that means the first point is that flux crossing the surface will be equal to what total charge within the surface, and the charges can be distributed uniformly or non-uniformly, and the surface, it has to be what a closed surface. So it does what closed surface. That is what we have been discussing. Okay, and yesterday we were able to discuss the application of Gauss law, applications of Gauss law in finding E due to point charge. So now we are left with finding E due to line charge, okay, and sheet of charge. Okay. How the Gauss law is useful in finding the field intensity.
Excuse me, sir. Sir, you are not audible, sir.
Excuse me, sir. You are not audible.
Hello. So, are you able to hear me? Hello.
Yes, sir.
Yes. So I think we have started here. So, Gauss law. I think this slide you were able to hear.
Yes, sir.
Yeah. What about this one? Yeah. So this is what we have discussed yesterday. So we are having a charge Q which is inside the sphere, and these are the flux lines which is crossing the surface of the sphere. And if you consider a small surface, means ds on this one, and it is making an angle theta with respect to the flux lines, so you will be able to deduce the expression for the flux that is equal to what the charge enclosed. So phi is equal to what q here. So you can write phi or psi depending on the context. So this is the expression what we have derived yesterday. That means we were able to prove that the flux lines, which will be exactly equal to the charges enclosed by the sphere. Okay, and small information here. So this the radius of the sphere is r. So what happens to the flux lines, the amount of flux lines crossing the surface if I increase the radius like this? So what happens to the flux lines? Does it increase or does it decrease or does it remain the same? That's the question. So I'm increasing the radius of the sphere. So whether the flux lines increases or the flux lines decreases or the flux lines remains the same. Any guesses?
Same, sir.
Yeah, same. Same is the right answer because the amount of charge is not going to change. So irrespective of the size of the sphere, the amount of charge is not going to change. And as a result, even if you increase the radius, or even if you're finding the field of 100 times the r distance, so the field remains same. The effective field remains same due to the amount of charge which is present inside the sphere. So phi is equal to the flux. So that is the concept here. Okay. Yes, and also, so just check out here. Uh, in the first case, the flux, the charge was uh, present at exactly at the center of the sphere. In this case, I have moved the charge. I have moved the charge towards my left. So what exactly might happen to the flux in the first case and the second case? So in the first case, we know that the flux is equal to the charge present. And what happens in the second case, where I have moved the charge from center to my left? So does it remain same? Yes or no? Hello? So what is that I have done here? I have just moved the charge position inside the sphere. So what happens to the flux through the sphere? Any guesses? Hello?
Remains same.
Yeah, it remains same again because again the amount of charge present in the sphere remains same. As a result, the flux crossing through the surface of the sphere will remain same. So the conclusion is that, so irrespective of the radius of the sphere and irrespective of the position of the charge in the sphere, um, the field intensity will remain same, as well as, sorry, the flux density will remain same rather. Okay, next, come back to this point. So what is the difference between the previous slide and this slide? Any guesses?
So irregular shape.
Yes. So it was the previous one was a regular shape, a closed surface, and here it is a non-uniform closed surface. The previous was a uniform closed surface, and here it is a non-uniform closed surface. So here also same thing. In the first case, the charges will be equal to what the flux. Okay, in the first case. So what happens in the second case? My right side figure, the figure on my right side. So whether it will be same or not. Just check out the figure here. Any guesses?
Remains same.
No. So here your flux lines is equal to what charges. Here the flux lines will not be equal to what charges, because you are having a hole here. Okay, this is the hole on the closed surface. That means the closed surface is no longer closed here at this point. So what you have thought here is a closed surface. It is no longer closed. So as a result, there is some opening here. So due to this opening, so you will not be getting the flux lines equal to what the charge is present. Okay, some of the lines would escape through this hole. That is the understanding here. So the Gauss law is applicable for what? The closed surface. Okay, so here the surface is open at this point, so you'll not be having means the flux equal to the charges present here. So got the clarity? Yes or no? Yes. So this is what we have discussed so far. Now we shall come back to some the application part. So in that we have seen application of the Gauss law. Okay, for determination of field due to point charge. So what was the equation here? Yesterday we have derived. So there's a point charge derivation we have discussed yesterday. So that is equal to the same thing. That means we have proved that one. So it is equal to Q by 4 pi epsilon naught r square into air cap point due to point charge. So E vector is equal to, it is nothing but D vector by epsilon naught, that is equal to Q by 4 pi epsilon naught r square into AR cap. This is what we have derived. Okay, so now we shall apply Gauss law to find field at a point. Okay, so we shall apply Gauss law to find field at a point, okay, due to an infinite line charge. Infinite line charge. This is the next application. This is the first application. This is the second application. So to find field at a point due to an infinite line charge. Okay. Yes. Just take down. To find field at a point due to an infinite line charge. Yes. Now just this is my line charge, which is on the Z axis or X axis or Y axis. You can take it as a reference. So in my case, I'm just taking it as a line charge. Clear? So I'm just showing here. So this is my line charge. Okay. So and it is uniformly distributed line charge. The charge is uniformly distributed along the line. That means it is the charge density is same. Charge density is same, and the line charge. So we have discussed uh, during the concept during the discussion of electric field due to line charge. The same concept holds good here also. So you'll not be having any field parallel to the line charge. Okay, so you'll be having a field perpendicular to the line charge, but not parallel to the line charge. Okay, so the line charge density is also given to you. That means it is of rho L. So we are required to find field at a point P. Field at a point P located at a normal distance r from the line charge. You can follow my screen. So there is a point P, okay, which is located at a normal distance r from the line charge. That means I'm interested in finding electric field at the point P, which is situated at a distance r from the line charge. So what we can do, we can just assume hollow right circular cylindrical surface. Okay, so we can assume that there is a cylinder, hollow cylinder, okay, of radius r and length L. Okay, I repeat. So we are assuming that there is a cylindrical surface of radius r. That means, so I am interested in finding field on the surface of what? Surface of a cylinder whose radius is r, whose length is L. Okay, so with both of its ends closed, okay, so that is what we are assuming now. So we are assuming that the first point, we are assuming that there is a hollow cylindrical surface, okay, cylindrical surface of radius r and length L, and whose ends are closed, okay, and also we are assuming that line charge is on the axis of the cylinder. Line charge is on the axis of the cylinder, so that the P point is lying on the surface of the cylinder. Okay, this closed surface is nothing but your Gaussian surface. Okay, so I repeat here the point. So what we are doing here, so we are assuming that a cylindrical surface r is radius of cylinder, L is length of cylinder, okay, P is on cylinder, and cylinder is closed on both sides. So both ends are closed. Okay, so that is why this surface is nothing but your um, Gaussian surface. Okay, so what is that we have to do? We have to find E now using Gauss law. That means we should find the D. We should find the D, that is nothing but your flux density, and you can make use of that flux density to find phi. Okay, so and from phi you can find the total charge. Okay, that is nothing but the flux lines crossing the surface of the cylinder here. Okay, so what exactly might happen here? Just follow me here. So we know that the D flux density will be at point P. So D is what? The flux density at point P. Okay, and all points on the curved surface are same distance from the line charge. So do you agree? So this is the curved surface of the cylinder, and that will be at the same distance from the line charge. That means it is equal to R. That means the radius of the cylinder. So the flux density is constant over the surface and is equal to D. So D is constant. So along the curved surface of the cylinder, D is constant. That is the second point you have to understand. Why it is constant? Because the surface is at the same distance at all points. Okay, so from the line charge. Therefore, so if you consider an elementary area like ds, okay, so you can write d psi as d vector into ds vector. This is our dot product of flux density and the surface vector. Okay, so let me write d vector here. So d vector is equal to, so d into the unit vector perpendicular to the line charge. That means the d vector and the field will be parallel always, as per our discussion. So the flux density and the field intensity will be in the same direction. So the field intensity will be perpendicular to the line charge. So the vector perpendicular to the line charge is your what? AR cap. So I'll write as what? AR cap. Okay. So and also ds vector, your ds vector is equal to ds into, so nothing but a normal to the vector we have to find. So the normal to the surface, we have to find. The normal to the surface is nothing but your n vector. Okay. So AR vector is a unit vector which is giving the direction of the field. N vector is the unit vector which is perpendicular to the surface at point P. You can take it as. Okay. So therefore, so your d phi, or sorry, d psi becomes equal to d into ds into AR cap into n cap. Okay. So d into ds into AR cap into n cap. So AR cap into n cap is nothing but what? Unit vector. So unit vector, and here also unit vector whose magnitude is 1, and they are actually acting in the same direction. They are actually acting in the same direction because the E vector and D vector along the same direction, so they are parallel. Therefore, the angle between them is 0. So therefore, you can take it as magnitude as 1. So your d psi is equal to d into ds. Okay. So this is what the flux equation. Okay. So now let's continue from here. So your d psi is equal to d into ds. So now I want to find, there are three surfaces now. Okay. So there are three surfaces. So you have to find d phi along three parts here. So one on the top surface, top of the cylinder, and bottom of the cylinder, and the curved surface, entire curved surface. Okay, there are three things you have to find out. So on the top side, what exactly the flux lines crossing, and on the bottom side, that is flux lines crossing, and on the curved area, that is complete curved area. So you are required to find out the flux lines. So let this be what? D phi 1, d psi, that is d psi 2, and psi 3. Okay, so just follow me here. The d phi, the d psi 1 and d psi 2 are here. That is the bottom as well as the top. So how the field will be? The field will be 0 there. So because, just follow me here. So you'll be having the flux density like this. As a result, you'll be having the field lines like this, and you will not be having the field lines parallel to one. So and E like this. So E is absent here because this lines are parallel to what the lines of charge. So obviously E is 0. So when E is 0, then E cylinder, there will be no cross. Zero. So we are left with only finding d psi 3. So the d psi 3 is nothing but curved area, only the curved area. Okay. So let me solve for d psi 3. D psi 3 is equal to, so d into, okay, ds. Okay, ds. This ds now is the surface area of the curved portion. Okay. So nothing but curved area. Okay. So let me find the total psi 3 now. That is nothing but is equal to d psi 3. Okay. Integration of d into ds. So this is how we have to find out. So now if you do it, so what is the um, area of the curved surface? That is the next question. So it is nothing but d psi 3, that is equal to, so d is constant. Let us take it outside of the integral later. So what is the area of the curved surface? Can anybody let me know? So you've got a cylinder like this, okay, and this is the R and this is the L. I want to find area of this cylinder.
2 pi RL.
Exactly. So it is the circumference is what, 2 pi R, and the length is L. So it is nothing but 2 pi RL. So your psi 3 is equal to d into 2 pi RL. So d into 2 pi RL. So this is what the expression for what the flux lines, which is crossing the surface area. Flux lines crossing the surface area. Okay. So if you just use this one, to find, for example, Gauss law, your q will be equal to phi, and that phi will be equal to phi 1 plus psi 1 plus psi 3, and this is equal to what, psi 3, and this is equal to 2 pi RL, and this will be equal to what, q. Okay. So if you just use this one and simplify, you will get E as rho L by 2 pi epsilon r into a r cap. So this is what the field intensity at a point due to what, the charge. Okay. So you just have to make use of uh, uh, so equation here for what is Q in terms of charge density, line charge density. Q in terms of line charge density.
Royal into L.
Yes. Rho L into L, and use this one, and you will get the answer. Yes. So R is constant here. L is varying from 0 to L. So just simplify it, you get this expression. So this is the application of Gauss law in order to find the field intensity due to what, line charge. Clear? So any doubts here? So small derivation what we have done. Next we'll move on to find E due to this is E due to sheet of charge using Gauss law. Okay. Yes. Just follow me here. So what is that you are having? You are having a infinitely charged sheet of or plane here. So infinitely charged plane along like this. Okay, it can be on XY plane, it can be on YZ plane, it can be on XZ plane also. So I'm not particular about the on which plane on which plane the sheet of charge is. We are interested in finding the field at a point, the field at a point due to the infinite sheet of charge. So using Gauss law again. So for that again we are assuming a again a cylindrical surface like this. Okay. So cylindrical surface with both ends closed, and here just follow me here. Length r, which is symmetrically stretched on both sides. So for example, here from this point onwards, to the left side, it is r, and from this point onwards to the right is r. So r is the length which is symmetrical on either side of the plane. Okay, r is the length of the cylinder. Okay, symmetrical on this plane, and also we are having p on one side. We are having p on one side like this. So this surface is nothing but your Gaussian surface. Surface is nothing but what? Gaussian surface. Okay. So now follow me here. So what is that we have assumed? So we have assumed that again a cylindrical surface. Okay. So r is not the radius here, r is the symmetrical length. Symmetrical length on either side of sheet of charge. Okay. Now, just follow me. This is what the ends of the and on the left hand side. At this point, at point P, I am interested in finding the field, okay, due to this sheet of charge. Okay, so let P be on what? Flat end, not on the surface. Okay, in the previous case, we have taken P on the surface. Here we are taking P on the flat end. Okay, one of the flat end I am taking on the right side of the sheet. So on the flat end. Okay, so what exactly the flux lines crossing the flat end? So what exactly the flux lines crossing the flat end? As a result, as per the discussion, the field will be what? Again, normal to the sheet, not parallel to the sheet. So the field will be what? The D as well as E will be what? Normal to the charge, not parallel to the sheet of charge. So it is perpendicular to what? The surface ds. Okay. So the direction of field and the direction of the flux density will be normal to the surface, so not parallel to the surface charge. Okay, that is what we have to understand here. So from here we shall just do some extension here. So flux lines crossing will be equal to what? the dot product of the flux density and the surface vector. Okay, so the surface vector, okay, is nothing but d into ar vector, and that is a field vector. So ds vector is nothing but what? Ds into the normal vector. So this is a normal vector. This normal vector is again parallel to what? The unit vector along the field. So as a result, so you're getting what? N cap. So if you multiply ar cap and n cap as before, it will be what? Equal to 1. So therefore, your d psi is equal to d vector, that is a d into ds into ar cap to n cap. Okay. So finally, d psi is equal to d into ds. Okay. So what is this ds here? So what is this ds? So ds is the area of the flat surface. Area of the flat surface. Area of the flat surface. So that is what it can be denoted as A. It can be denoted as A. So I will denote this as A. And again, will there be any field or flux along the surface? That's the next question. Will there be any field or flux lines along the face of the cylinder? Any idea?
No, sir,
Why?
because it will be perpendicular to the field.
Perpendicular to the
Electric field.
Correct. Yes, yes. So it will be parallel to the nothing but sheet of charge and perpendicular to the electric field. So you'll not be having any field of flux lines crossing the surface. So only the flux lines will be crossing the flat ends of the cylinder. Okay. So this is what to understand here. So the phi will be due to what? 3 parts you can assume. So for example, top, phi bottom, and phi surface. And in this case, phi surface is equal to 0 here. In this case, the phi surface will be equal to what? 0. And phi top and phi bottom. So the flux lines will be leaving the top or radiating from the top surface as well as the bottom surface. So we are interested in finding that phi at the top as well as the bottom. Yes. So phi is equal to, so phi 1 plus phi 2 plus, that means phi top plus phi bottom plus phi surface. So this will be what? 0. So as a result, so phi will be equal to phi ds is not equal to what? A. So integration of the small surface along the top surface and the bottom surface, which I am writing as what? A. Therefore, your phi is equal to, so d times A here for top surface and d times A here bottom surface. So totally there will be what? 2 times dA. This is the total flux leaving the surface, top surface and bottom surface. Okay. Yes. So we know that phi is equal to Q here. There is a charge enclosed. So Q is nothing but rho into A. So therefore, if you use this one, you'll be able to solve for E vector is equal to rho s by 2 epsilon naught AR cap. Okay. So this is what the expression for field intensity. So I'm making use of this and I'm equating, and then I'm simplifying for what? This one. Okay. Yes. This is what expression for sheet of charge, field intensity. Field intensity due to what? Sheet of charge. So any doubts here? So using Gauss law, we have been able to find out the flux lines, and from the flux lines we are able to what finding the field intensity due to point charge, due to line charge, due to sheet of charge. Clear? So this is how Gauss law is applicable to find like this. So any doubts up to this point? If it is clear, please type 0 in the chat box. Yes. Next concept. So we have to find the intensity or the application of Gauss law to find E at point due to a shell of charge, spherical shell of charge. Okay. Yes. So we are applying Gauss law. Again, the interest is to find the flux lines, and from flux lines we have to find out the intensity. Okay. Yes. This is E at a point due to a spherical shell of charge. This is a spherical shell. Spherical shell means what? It's a hollow shell. Okay. So there will be somewhat uniform distribution of charges. Uniform distribution of charges. Okay. And we have to find the intensity at 3 points. So one on the surface. Okay. Next, outside the surface, the surface. So if we're having a shell like this, you'll have to find E here, point A. You have to find B, E at C. So A is outside the shell, B is on the shell, C is inside the shell. Okay, this is what it means. So the surface, outside the surface, and inside the surface. These are the 3 items we have to discuss using Gauss law. Okay. So any doubts there up to this point? So let me discuss the first concept. Yes. So you have got a spherical shell of charge here. So what we are assuming here, we are assuming that uniform charge distribution on its surface. That means we are having some uh, charges on its surface like this. Okay, this from charge surface. I am interested in finding at this point P. Okay, so this point P is at a distance of R. R is radius of the shell. The radius of the shell, and R is greater than R here. Okay, got it. So the Gaussian surface, thing but a concentric sphere. This is the dotted line, concentric sphere of radius R, which passes through the point P. The flux lines definitely radially move outwards, and that will be normal to the Gaussian surface. So the Gaussian surface is ds, okay, and the flux lines will definitely move radially outwards. Okay. So now, what exactly the flux through an elementary area? That is given by what? D and ds vector. That is nothing but what? D into ds into ar cap into n cap. That is nothing but the frequency will remain same and ds. So the total surface area ds is of the sphere. It is nothing but what 4 pi r cube d into 4 pi r cube. Okay. So this is exactly equal to q. This shape you can find E. So E is equal to what? Q by 4 pi epsilon naught R square. Where we is equal to what? Epsilon naught into E. That's all. Yeah. So this is on the point B, which is outside the shell. So now what happens? The second case. So the P is on the shell. So P is on the shell. Everything remains same except for this R. So R is what? Distance. Okay. Here the R is what? The radius. So same equation you will get. So E is equal to, so it is nothing but Q by 4 pi epsilon naught R square A R cap. That's all. Clear? The last case. So will you be having any charges inside this shell? That is the next question.
No, sir.
No, sir.
No. Why? Why? It is a hollow sphere, correct? It is a hollow sphere. So you'll not be having any charges inside this shell. Outside the shell will not affect the flux lines. Clear? So as a result, the field will be what? Zero inside the shell. Clear? The charges outside the shell will not have any effect on the field. The charges will come and leave. That's all. So that is the Gaussian surface. That is the property of what Gaussian surface. The field at any point inside a charged sphere is 0. Clear? Yes. So this is what the one more application of Gauss law. Okay. So now what happens here? Just variation you can find here. So this is my field intensity and this is my. So that means as the distance is increasing, what happens? So for example, up till it becomes equal to what? R, the field intensity is 0. So this is R. And after that, what? The field intensity decreases and becomes E. So as R tends to increase, the E tends to decrease. Okay. So this is what the variation of field intensity with respect to what R. This is what is shell. Okay. So and this is R. So when R is exactly equal to R, there will be somewhat field intensity. And when R is not less than, is not greater than R, so the field intensity will be 0. This is nothing but in the sphere. This inside the shell. Okay, and this is at the shell or on the shell, and this is outside the shell. Okay, so this is the region where your intensity is varying. Okay, yes. So any doubts here up to this point? So what you can expect from exam point of view? From exam point of view, you'll be given what different scenarios. So you'll be asked to apply Gauss law in finding what the electric field. Okay. Yes. So what I will do, I'll just stop at this point. So we shall continue in the next class. I'll let you know the details of the next class shortly. So we are planning to have some additional classes during this period because we'll not be having any labs as of now. So we'll be planning some additional classes. So we'll let you know the details. So at this point, I will stop. So any doubts, you can hang on the chat box and ask. Thank you.
Thank you.
Thank you.